สวัสดีค่ะจุฬาลงกรณ์มหาวิทยาลัยและก็ Peace Foundation ขอต้อนรับทุกท่านเข้าสู่การปาฐกถาพิเศษนะคะสำหรับวันนี้ขออนุญาตที่จะเรียนเสนอในขั้นตอนของการบรรยายเป็นดังนี้ค่ะเวลา 14 นาฬิกาตรงนะคะก็จะเริ่มโดยการกล่าวต้อนรับโดยผู้อำนวยการของสถาบันวิจัยของวิทยาลัยปิโตรเลียมและปิโตรเคมีจากนั้นก็เป็นการกล่าวต้อนรับโดยPeace Foundation นะคะแล้วก็ตามด้วยธนาคารกสิกรนะคะจากนั้นก็จะเป็นการแนะนำ Professor Molina ให้พวกเราได้ทำความรู้จักกับท่านว่าประวัติของท่านการที่ท่านได้มีความตั้งใจจนกระทั่งมาถึงจุดที่ท่านประสบผลสำเร็จเป็นที่ยอมรับทั่วกันจากการที่ท่านทำงานโดยไม่ได้มุ่งหวังอะไรเลยประวัติที่น่าสนใจของท่านคงอยู่ที่ว่าท่านมีพลังขับดันอย่างไรที่เราจะได้เรียนรู้นะคะว่าตั้งแต่เด็กอายุน้อยๆจนกระทั่งท่านเติบใหญ่แล้วมีพลังขับดันแล้วก็มีความมุ่งมั่นที่จะร่ำเรียนในเรื่องของวิชาทางด้านเคมีนะคะดิฉันก็จะเป็นผู้แนะนำให้ทราบในรายละเอียดจากนั้นก็คงจะกราบเรียนเชิญ Professor Molina บรรยายในวันนี้นะคะเกี่ยวกับเรื่องของผลกระทบกิจกรรมของมนุษย์ต่อสภาพภูมิอากาศทางด้านเคมีนะคะการบรรยายจะดำเนินไปถึงเวลา 15:30 นาทีจากนั้นเราจะเปิดโอกาสให้มีการซักถามซึ่งการซักถามมีได้2 กรณีนะคะคือเรามีไมโครโฟนเตรียมไว้หรือไม่ท่านอาจจะเขียนคำถามในกระดาษแล้วก็จัดส่งเราจะมีหน้าที่คอยตามแล้วก็เก็บคำถามคำถามจากนั้นก็จะส่งคำถามโดยตรงให้กับ Professor Molina เพื่อท่านจะได้ตอบคำถามในสิ่งที่เราต้องการในรายละเอียดซึ่งอาจจะเป็นเรื่องที่เป็นแรงจูงใจของท่านหรือเป็นเรื่องของทางวิชาการก็ได้ค่ะ Good afternoon, ladies and gentlemen. It's a great pleasure for Chulalongkorn University to have Professor Molina with us today. We are so pleased that we have a chance to more close contact and learn more, not only from his work, but from his background and his family life and his lifetime also. With this special event, may I have the honor to call upon Director, Petroleum and Petrochemy College, to give a welcome speech. Yes, Associate Professor Dr. นันทิยาจารุมาศยานุมาศขอกราบเรียนเชิญค่ะอาจารย์
Honorable Professor Mario J. Molina, Mrs. Molina, the Chairman of International Peace Foundation, representative of Kasikorn Bank, distinguished guests, ladies and gentlemen. It is an honor for Chulalongkorn University to once again lend its collaboration to the International Peace Foundation in hosting this second and final event in the series Bridges Dialogues Toward a Culture of Peace. This series is aimed to bring together people from all walks of life and academics of various interests into one place where they could share knowledge and understanding and create meaningful discussion, which will hopefully be a stepping stone to a climate and culture of peace. It is also my great pleasure on behalf of Chulalongkorn University community to welcome Professor Mario J. Molina, the 1995 Nobel Laureate for Chemistry, whose findings of the influence of chlorofluorocarbons, or CFCs, on the atmosphere and whose decision to communicate these findings not only to other scientists but also to policymakers and the media have made a profound impact on the global environment and have improved the public awareness of the CFC ozone issues and its serious consequences for the atmosphere. During the past few decades, there has been strong evidence that human activities have led to worsening air quality on broad regional scales. This deteriorating air quality problem is expected to reach global proportions in the coming decades, with potentially detrimental effects on ecological systems and on human health. Professor Molina's lecture on the impact of human activities on the chemistry of the atmosphere will be directly relevant to and useful for people of all regions and races. I would like to express my sincere appreciation to our distinguished speaker, Professor Mario J. Molina, not only for the lecture he is about to deliver to this audience, but also for providing the opportunity to fellow scientists, educators, and interested people to avail of his expertise and insight. I would also like to take this opportunity to express our thankfulness to the International Peace Foundation and Kasikon Bank, which has helped to make this lecture series possible. Thank you very much.
For a welcome remark, may I have the honor to invite Mr. Uwe Morawetz, Chairman of the Board of the Director of the International Peace Foundation. Please, Mr. Uwe.
The basis for peace is education and the right to learn to listen to your heart. This is why the International Peace Foundation works together with major universities and schools in Thailand to bring some of the best spirits in the world, 27 Nobel laureates, to the kingdom to build bridges and establish an ongoing cooperation which may contribute to an education reform and to the inclusion of peace programs in the curricula of these universities and schools. A reform in which education is not only a platform to learn answers by heart and to merely serve consumerism and materialism, but to find the right questions that guide students to find a profession which matches their vocation. A profession that corresponds to their individual talents and abilities, which may lead them to a life fulfilled with sense and social responsibility. Answers are not given, they lie within, and the key to find them are the right questions. Knowledge without wisdom leads us to nothing but separation. Theory without practice and intellect without intuition may lead to catastrophic results. Therefore, the International Peace Foundation promotes an intercultural and transdisciplinary approach towards peace, and as its basis, education, in which representatives of science, politics, economy, culture, religion, the media, and youth share their viewpoints, listen to each other, and find mutual ways of cooperation through which the young generation can get a more inclusive, interconnected, and comprehensive idea of the world in which we live in and which we create constantly anew. โลกนี้จะใช่โลกที่เราต้องการอาศัยอยู่หรือไม่นั้นขึ้นอยู่กับตัวเราและทางเลือกที่เราจะตั้งคำถามเพื่อค้นหาคำตอบซึ่งไม่ใช่คำถามที่มีคำตอบอยู่ในตัวแล้วการแสวงหาคำตอบขึ้นอยู่กับคำถามไม่ใช่กับคำตอบที่เตรียมไว้ก่อนแล้วการศึกษาเป็นเครื่องมือที่จะค้นหากลุ่มทรัพย์ภายในที่จะเชื่อมปัญญากับความรู้และที่จะทำให้โลกนี้น่าอยู่ยิ่งขึ้นสำหรับพวกเราทุกคนการศึกษาไม่ได้เป็นแต่เพียงเครื่องมือที่จะช่วยให้เราเผชิญการเปลี่ยนแปลง หากแต่เป็นเครื่องมือเพื่อการเปลี่ยนแปลงผมขอขอบคุณธนาคารกสิกรไทยและจุฬาลงกรณ์มหาวิทยาลัยตลอดจนผู้สนับสนุนและผู้ร่วมงานทุกคนสำหรับความร่วมมือร่วมใจในงานนี้ I'm especially grateful to Professor Mario Molina, who came to Thailand without any honorarium to support the events, and I now look forward to his keynote speech and his important contribution to build bridges. ขอบคุณมากครับ
For welcome remark, Kasikorn Bank, you take this chance to share our appreciation to Nobel laureate Professor Molina. May I have the honor to call upon Kun Janjari Buranawet, First Vice President Cooperative Communication and Administration Department, Kasikorn Bank. Please, Kun Janjari.
Director of the Petroleum and Petrochemical College, Chulalongkorn University, Chairman of the Board of Directors, the International Peace Foundation, and distinguished guests. In celebrations of humanity without borders and admiration of Thailand as a peaceful country, Kasikorn Bank is proud to sponsor speeches by 18 Nobel laureates in 5 months, from December 2004 to April 2005. Each Nobel laureate will deliver his or her keynote addresses at various universities all over the country as part of the International Peace Foundation's Bridges, Dialogue Towards a Culture of Peace project. On behalf of Kasikorn Bank, I am honored to present Professor Mario J. Molina, Nobel laureate for chemistry in 1995. Thank you very much.
Now, the auspicious time has come to us. So exciting that how much we have time to more closer to Nobel laureate. Yes, I, as an MC of this special event, it's a great honor to me to have the honor to bring all of you more closer to Nobel laureate for chemistry in 1995, Professor Mario Molina, with the special lecture on air quality and climate change. Professor Molina shared his Nobel Prize with Professor Sherwood and Professor Cruzen for the work in atmospheric chemistry, particularly concerning the formation and decomposition of the ozone. That is to say, our salvation from a global environmental problem that could have catastrophic consequences. The ozone layer that actually heals small but weak point of the biosphere have been taken care by 3 of them. It's more interesting to look more close to lifetime of Professor Molina, because after I study his background, I'm so impressed and appreciate his strong will and determination, because his study, since he's entering the high school, he started excitement with a primitive microscope. A little one maybe just recall his remembrance about this. He looked through the microscope with excitement when he can see gone through the amoeba inside, and then he turned or convert his bathroom to laboratory and spent hours and hours playing with chemist toy. With full support from his parents to fulfill his decision to become a research chemist, Professor Molina was sent to Switzerland since he only 11 years old. And further his study, he received the first degree from Mexico in chemical engineering, and then postgraduate degree from University of Freiburg, Germany. And further he studied in doctoral degree in physical chemistry and postdoctoral at University of California with different campus. And at Berkeley, he pointed out that the time was counted among the best of among the best, because at that place he changed his life because he had been met his closer co-worker and later become his wife. Yes, please welcome Miss Louisa Tan. And later on, yes, as we already realized about the Nobel Prize in chemistry in his life, I would like to bring more of all of you to more close to Professor Molina with his academic career. Start with assistant professor at the National University of Mexico and assistant associate professor at University of California, USA, and at present he is professor of chemistry and professor of earth, atmosphere, and planetary science at Massachusetts Institute of Technology, USA. Of course, he has been intention himself and stated himself as a chemist since he's a little boy. But the condition that led him to can save our world, we can say that, to realize that it appear ozone hole at some part in the stratosphere. The initial condition for this is joining the group of Professor Sherwood, who offered the one project that integrate him to most consist of finding out the environmental effect of concern, very inert industrial chemical, CFC, chlorofluorocarbon, that we already know that it has been used in a refrigerator or in the can. It's already banned after his finding. In 1973, Professor Molina discovered the threat of CFC posed for the sensitive ozone layer. 1 year later on, he was assisted by the media, brought the problem to attention of the public. And surprisingly, in 1985, the first ozone hole became visible over Antarctic. This will remind some activity of scientists who have been done the work, how vision of the scientists have been give the answer to the world. And in 1987, United Nations Montreal Protocol was signed in Canada. Yes, 22 years after the initial condition work with Professor Sherwood, Professor Molina received Nobel Prize in Chemistry in 1995 for his work on the chemical process involved in the formation and decomposition of the ozone. His finding led the Montreal Protocol, an international agreement that called for a complete ban on CFC production from 1996. I'm so impressed about environmental concern of Professor Molina. As a chemist, he always concerned about society and people around him. You will get in touch more in detail during his lecture or during you ask the question to Professor Molina. Since he's a little boy and during the bachelor degree study, he realized a negative side of science, that chemical can be dangerous. And he stated himself strongly to say that I want to be involved with research that was useful to society, but not for potentially harmful purposes. Moreover, the annual concern from Professor Molina is his interest in environmental issue, and then he found out that human activities will potentially lead to a very worrisome situation in the environment. And of course, from his long experience, he always emphasized in many places in the world to say that it was not enough to just do the science, but it was important to try to do something about it. Like closer to some just little part that the others show their appreciation and recognition to the work that Professor Molina have been done along his life, besides his co-worker who full support him. In 1983 is Tyler Award, and 1987 the Eisen Award of the American Chemical Society, and 1989 the NASA Medal for Exceptional Scientific Achievement, and Pew Scholar on Conservation and the Environment, and yes, 1995 Nobel Prize in Chemistry together with Professor Frank Sherwood Lauren and Professor Paul Cruzen. After that, Heinz Award for the Environment, Doctor of Science Honoris Causa from Tufts University and from Peking University. And of course, Volvo Environmental Prize also. Yes, I believe that we are more closer to Professor Molina now, thanks for good science, scientific understanding of the ozone hole problem that saved our Earth. And I do in place, and I believe that all of the audience very much appreciate his stage about I want to do research that is useful for society. Because of his career, he emphasized that I now see teaching and research as complementary, mutually reinforcing actives. Since 1943, further his lifetime until 2004, today, here at Chulalongkorn main auditorium, we have a chance to more closer to Professor Molina, Nobel laureate. How much I impressed to his background and how he continued his strong will and determination in his life. May I have the honor to call upon Nobel laureate, Professor Molina, to give a lecture on air quality and climate change. Please, Professor Molina.
Is this working? Hello? Oh, okay. I want to start by thanking our... is it on? A little closer. There we go. Okay. Okay. Good afternoon, everybody. I hope you can hear me now. Want to start by thanking our Master of Ceremonies for her very kind introduction. And I also want to thank the International Peace Foundation for organizing these events and inviting me to participate in them, and of course the Chulalongkorn University for inviting me also and making it possible to talk to you this afternoon. I will be talking about some environmental issues, some research I have been involved with now for several decades, as you just heard. And let me start by pointing out how our planet looks like from space, just by showing you a photograph taken just in the middle of the 20th century, when we first began to realize that the activities of society were beginning to affect not just locally the environment next to large cities or next to population centers, but the entire planet began to be affected by human activities. One of the ways to see that humans can affect the environment is to observe how thin the atmosphere of the planet is. You can hardly see it in pictures like this except for the clouds. But the atmosphere functions in such a way, because of the winds, because of the climate as we know it, the weather, that if some chemical substances are released anywhere on the surface, be it from natural causes or because of activities of society, such species moves on a time scale of months and covers the entire planet. It takes months to mix within the northern hemisphere if a species is released in that hemisphere, and it takes about a year or two for anything released on the surface to mix in the entire planet. What happens is, fortunately, the atmosphere has a very efficient cleansing mechanism. So there are many gases and also particles that are emitted, some by natural processes, as I was just talking about, and rain and clouds normally remove all these emissions so that they do not accumulate. However, there are certain gases that are long-lived, that are not removed fast by clouds, and if such substances can remain in the environment for more than several months, some of them remain there for years, even for decades, those substances really mix throughout the entire atmosphere. So it is just in recent years, in the last 2 decades of the 20th century, that we became aware of the potential of human activities to affect the environment. I have a list here of some important challenges that we have in this century, challenges connected with environmental problems. Many of the ones listed here at the top, issues concerning water, water availability, water quality, depletion of natural resources, for example, deforestation or overexploitation of fisheries, availability of fish in the oceans, or disposal of waste. Many of these worries, we tend to think of them as local issues. They occur close to the sources of the problem. Even air quality. We know that air quality can be very much affected in large cities. Bangkok is one example. Mexico City is another one that I will be talking about. But the issues I was just describing with this picture of the planet, they have to do with changes that happen to the entire atmosphere, the atmosphere all over the planet. So I'm going to spend a little bit of time talking about each of these issues. I will start talking about stratospheric ozone depletion issue, as you heard a few minutes ago. That's the issue I first became involved with in dealing with the environment. To explain this problem again, the problem of the stratosphere, which I started to worry about in the 1970s, I'm going to go back in time to take a little bit of historical perspective towards the beginning of the 20th century. After, of course, the Industrial Revolution, as you know, was very successful, improving our standard of life. We now have a life expectancy that is more than twice what it was at the beginning of the 20th century. So I'm showing you an advertisement, an ad that appeared in 1911 when refrigeration, home refrigerators first became available. That's because electricity became available and so were electric motors. Before these devices became available, people had to live without refrigerators or perhaps just using ice boxes. How do these devices work? Well, you have a compressor and you have a refrigerant, a fluid that can be readily converted from a liquid to a vapor, and you compress a vapor, you get the liquid back. And the early refrigerators used ammonia or sulfur dioxide as these refrigerants. And these are very toxic species. And there were a number of accidents that occurred because some of these refrigerators broke down and they were in small living rooms where families had to breathe these toxic fumes, and hence accidents happened. So it became apparent in the 1920s, 1930s, that something new had to be invented. And a number of people worked on trying to solve this problem of toxicity. And here I'm showing you a picture of one person that worked on that you probably all recognize, Albert Einstein, because we are celebrating this year, of course, Einstein's discoveries that were so important. But one that is not well known is that he also worked with one of his colleagues, Leo Szilard, on developing different type of refrigerators, which indeed work, but they turn out to be not very practical. And so the solution to the refrigeration problem that I'm talking about did not go along the lines that Einstein envisioned with different cycles, adsorption, desorption cycles, but rather again using compressors, very much the way the refrigerators work today, but not with ammonia or sulfur dioxide, but with some new chemical species. They were called miracle species, the so-called CFCs or freons. Those are species that are not toxic. So even if the refrigerator breaks down, you don't have a problem breathing those gases. So what happens, though, is that these miracle chemicals began to be produced in large quantities because they were very useful for other applications, for example, to make plastic foam, or also as propellants in spray cans, because you need a liquid inside the can which evaporates when you press the button, and then you can spray whatever you want. But you're going to breathe the gases that escape from the can, so you cannot use ammonia in a spray can, of course. Now, what happens is so much of these chemicals began to be produced in the 1940s, 1950s, that they began to accumulate in the environment. And they are so stable that rain and so on did not affect them. So it was possible to measure the presence of these compounds that are not natural. They were entirely of industrial origin all over the planet. So it's because of this that, together with my colleague Sherry Rowland, you saw a photograph of him earlier on, that in the 1970s we decided to find out. We asked a question: what happens to these gases once they are in the atmosphere? We knew that rain would not affect them. We knew that chemical reactions in the lower atmosphere would not affect them. So what we concluded is that they would eventually go to higher altitudes, where they would then be destroyed by short wavelength radiation from the sun. And why at high altitudes? Because this radiation does not penetrate to the Earth's surface, because fortunately our planet has an ozone layer. It's a natural layer. Ozone is a form of oxygen, as you know, that whose molecules have 3 atoms instead of the 2 atoms that normal oxygen has. And there's only a little bit of ozone, parts per million only, in the atmosphere, but enough so to prevent this radiation from reaching the Earth's surface, and that's what allowed life to evolve. Life could not evolve with this very harsh radiation that would break down molecules like DNA or so. However, when the CFCs move above the ozone layer, this radiation breaks the molecules, and some of the atoms that make up these molecules, like chlorine atoms, can actually affect the ozone layer very efficiently through an amplification factor. Chlorine atoms are recycled. So chlorine reacts with an ozone molecule and breaks it, and then other reactions happen and you get the chlorine atom back. So a single chlorine atom can destroy tens of thousands of ozone molecules. The natural ozone layer is also controlled by small amounts of nitrogen oxides. And Paul Crutzen, a colleague that you also saw a picture, that I understand he gave a lecture here in this auditorium, I think 1 or 2 years ago. He was the original discoverer of this way in which the natural stratosphere functions, and that laid the background for us to be able to then make a prediction. This is just a theory when we first postulated it in the 1970s. Nothing was happening to the ozone layer, but we suggested if CFCs continue to be used and produced, the ozone layer would be affected. And indeed, in the 1980s, in 1985, it became possible to measure that something quite dramatic was happening to ozone over Antarctica. We did not initially predict that. That's where the atmosphere is very cold. So there are measurements here from the ground, and here are measurements from a satellite. Different colors represent different levels. And over Antarctica, where it's very cold, these reactions that destroy ozone are particularly efficient. We now know that ozone is destroyed everywhere, but particularly over Antarctica, also over the Arctic and at other latitudes. Why do we call it the Antarctic ozone hole? Well, because here is what happens. These are amounts of ozone in this blue line that are present naturally in the atmosphere, most of it present in the stratosphere, altitudes close to 20 kilometers above the Earth's surface. But since the 1980s, what began to happen is that in the spring months, on a time scale of about a month, ozone then disappears practically at certain altitudes, which is where there are ice clouds. And when it disappears, more than 99% goes away. That's why we call it an ozone hole. At lower altitudes, at higher altitudes, where these clouds don't exist, ozone is not affected as much. We have ozone all the way to the ground, but normally it's all there. So the hypothesis that we put forward in the 1970s could be tested. Initially, it was not clear that this was caused by human activities, but many experiments were carried out with the scientific community, many experiments in the polar stratosphere over Antarctica, many other latitudes as well, and it became eventually very clear that this indeed was caused by the CFCs, by these chemicals. And this led, as you heard earlier already, to this international agreement. The scientific community was able to convince countries all over the planet, all over the world, to sign this agreement, which called for the phase-out, stopping the production of CFCs. Fortunately, because of these signs, it was possible to push society to develop other chemicals to replace the CFCs, so that we still have refrigeration, we still have spray cans, we still have plastic foam, but it no longer uses CFCs. There are some other products. Spray cans use hydrocarbons, refrigerators, some use ammonia nowadays, of all things, but they also use other compounds that have been designed not to reach the stratosphere or not to affect the ozone layer. So this is one example, a very important precedent we have of how society can solve a global problem. It is unfortunately the only example there is. That's the only global problem for which there is a successful international agreement. The ozone layer has not recovered yet, because the CFCs, these compounds, industrial compounds that are there, remain in the atmosphere for many decades. So we now have in the atmosphere compounds that were released earlier in the 20th century, and it will take several decades before they disappear. We can already see the CFCs going down, but the ozone layer will take several more decades before it recovers. So now I want to switch to another topic that also involves ozone. This is a picture of the air in Mexico City in the 1990s. Mexico City was the most polluted city in the world, perhaps, at that time. Fortunately, it's much cleaner now, but we still have a big problem, as I'll discuss in a moment. But what is this pollution? That's what we call smog. It was first really understood and analyzed in the city of Los Angeles in the United States, but Mexico City has a very similar problem. We know it has to do with the quality of air. Bangkok is another city that has a pollution problem. But this pollution, the main ingredients turn out to be two compounds that we worry about. And these two compounds are ozone and small particles. Ozone is the same species that makes up the ozone layer in the stratosphere. But in this case, ozone is produced from the emissions of vehicles, cars and trucks. There are three ingredients of this so-called smog. The three ingredients are gasoline or diesel fragments that escape to the air, nitrogen oxides that are produced by combustion. When you heat air, that as you know is made up of nitrogen and oxygen, if you bring it to high temperatures inside the engine of any one of these vehicles, it goes to very high temperatures when the fuel is burned. So at high temperatures, the nitrogen and oxygen combine, and you get nitrogen oxides. And the third ingredient is radiation from the sun. So the three ingredients together make ozone, which is a toxic species in large concentrations. We want it to be in the stratosphere, but you don't want to breathe it. And the other worrisome component of the atmosphere in a polluted place are small particles, particles of just a few microns or less in diameter that can penetrate into your lungs when you breathe them. So here we have results of satellite measurements, measuring nitrogen oxides over a number of cities, Los Angeles, Mexico City, Milan in Italy. And as you can see here averages of measurements different days of the week. And Sundays the levels go down. So what is very clear then is that this, one of the main ingredients of smog, is really emitted by the transportation sector, by cars and by trucks and so on, because the activities decrease on the weekends. In other cities, Beijing and Cairo, it doesn't really change that much. In Jerusalem, the effect is on Saturdays because of course, the Sabbath, the religion in. I just talked about air quality, but the problem when we talk about this large scale is that these pollutants are also contributing to changes in climate. But the main change in the climate comes from what we call greenhouse gases. Just briefly, you know how our climate functions. We get energy from the sun in the form of visible radiation that reaches the surface of the planet, except some amount that is reflected by clouds. And our planet loses energy at the same rate that it receives energy from the sun. No longer accumulates any energy, but it loses the energy in form of infrared radiation, and the atmosphere is not transparent in the infrared in contrast to the visible. And the species that absorb infrared radiation are called greenhouse gases. The most important ones are water vapor and carbon dioxide. There's a natural greenhouse effect which makes the surface of our planet to be, on the average, about plus 15 degrees Celsius. Without this blanket, without those gases, it would be much cooler, below zero, below about minus 18. If that were to be the case, the oceans would be frozen and we would have no life. So the greenhouse effect, the natural greenhouse effect, is very important for life on our planet. The worry that we have is that we're increasing the amount of these infrared active gases. And so here is a picture of what's happening to the atmosphere. If we go back 1,000 years, these are greenhouse gases, gases that are long-lived, that mix throughout the entire planet. carbon dioxide, you can just see how it is in this last century that the composition changed very dramatically. And other greenhouse gases, methane and nitrous oxide, show the same pattern. How do we know what the composition of the atmosphere was 1,000 years ago? We can analyze the air in small bubbles that are trapped in ice cores, in Greenland or Antarctica or so. In fact, we can go back not just 1,000, but 100,000 years to measure what the air looked like at that time. And it's very clear that these dramatic changes are very recent. Of course, the composition has changed. If we take a long view of 100,000 years, has also changed in the past. But that was connected with ice ages. The climate would look very, very different during an ice age. So what are the consequences? Well, the temperature is also changing. And here the worry is that this is the mean, the average over the entire planet. On any one part of the planet, temperature changes a lot, and you cannot be sure if the changes are natural or not. But when you average the changes over the entire surface, you can see this pattern of very recent climate change. The surface of the planet is warming up. And so we have a strong suspicion that this change is indeed connected with the changes in the chemical composition I just described. And I just want to give the following message. The climate of our planet is very complicated. The climatologists or people that study climate are not certain of how much more will the climate change if we continue releasing greenhouse gases. So what they can do is calculate probabilities. And this red curve is one representation of the probability that the temperature will change by so many degrees in this century. This is a problem of taking a risk. We don't need to be certain that the temperature will change this much. All we need to know is that there is a very large risk. And we have then, as scientists, we present these results, and as individuals, no longer as scientists, we have to make decisions whether or not to change our way of life, to prevent the possibility of these very large changes taking place. Why do we worry about these large changes? Because we would affect the hydrological cycle. We're already seeing much more floods, the rain coming in much more concentrated fashion, but also more droughts. Many parts of the planet are getting to be more dry. Sea level is rising, and there are many other consequences for agriculture and so on. So I just want to finish with this picture here, which is another curve, which shows a very sudden increase, just very recent, and that's human population. In this case, we go back thousands of years, 8,000 years. And the point is that it's because we have so many people on the planet that we're seeing all these recent changes that are very worrisome. If we understand the changes, we can perhaps work in such a way that we can prevent damage to the environment. The worry that we have is that only 1/5 of these 6 billion people that we have on the planet live in the developed world with high standards of living. And if the 4/5 that remain were to develop in the same way, we would have a very serious problem with all the emissions of everybody. We already have the problem of affecting the environment. So we have to learn, and learn fast, how to improve the standard of living throughout the world, how to improve the economies of so many countries that, with so many people that live in poverty. However, we need to have that improvement recognizing that there are potential environmental problems, but we know that there are solutions. We know that we can conserve energy. We can use energy much more efficiently. We can develop alternate forms of energy that do not release so much carbon dioxide, either using biomass or capturing the carbon dioxide or using wind. We have to use a variety of solutions. So there are ways to deal with the problem. I come back to the CFCs just to finish this. That's why that's an important example, because we showed how it was possible to preserve the benefits to society of the technologies that were developed earlier, refrigeration, air conditioning, spray cans, but it was possible to develop new clean technologies that do not affect the environment. So that's what we need to do, and that's why it's important for universities like this one to educate students to become aware that we're facing these enormous problems, and we have to work together with students all over the planet, face these challenges, and hope that we can work towards the improvement of society, preserving, however, a healthy environment for the benefit of future generations. Thank you for your attention. Yes.
Yes, now the floor is open for question, please. Any question right now? We provide microphone and a piece of paper. To warm up our atmosphere during the time I prepare, introduce my presentation to introduce you. Many persons surprised at how to fall in love in chemistry.
Say that again?
How to fall in love in chemistry.
Oh, well, yes, just to make a comment on that, I was, as a child, very interested in science, as you pointed out so nicely. And then what I learned in college is that it was not just very nice to see how nature functions, like I did when I was looking down on a microscope, but it is very, very rewarding to find out new things, to contribute to the development of new findings in science that nobody has seen before. But even more rewarding is when you can apply that so that you solve problems that are beneficial for society, and that's where the environmental issues come in. So the science sometimes gets very difficult, and it is nevertheless very important to persevere, to keep working on these problems so that one can actually have an impact. And it's also very important not just to do the science alone, but one has to work with governments, with different groups in society so that things actually happen. And that's a big challenge.
And a little bit further, which part of chemistry is charming to you? Maybe it will be inspire us to fall in love in chemistry like you in the future.
Yes, well, again, when I started, I was doing relatively simple experiments. I was fascinated with the way crystals grow, with the way chemicals can mix, and things that I could do as a child. Then later, when I went through college, I did more complicated experiments in which you use instruments just to see the results. But it is really fascinating to discover the natural world, and more so to invent new things. Okay, so it's extremely rewarding. Perhaps one of the largest rewards was to see how the Montreal Protocol eventually worked, because we saw that we had a real effect on the entire world. Yeah. Okay. I don't know if there are any
กรณีของคำถามนะคะขึ้นมาได้เลยค่ะหรือถ้าท่านใดที่จะใช้ไมโครโฟนได้เลยนะคะ Any question directly to microphone, please feel free to do so. We provide some of microphone.
Perhaps they could even do it in Thai and you can translate. Yes,
yes, they are already done.
Oh, okay.
I will try my best. Question, please.
Yes. Yes, let's see if it works. Yes.
Thank you, Professor, for the good lecture, enlightening lecture. I just wanted to ask you about the Kyoto Protocol, because many countries in the world have accepted it, but United States has not.
Right. Saying
that it's not practically possible and like it's something like politically biased. I'd like to have your views on this.
Yes, yes. First of all, let me say that most of you are probably aware that The same way the Montreal Protocol deals with the stratospheric ozone issue, the Kyoto Protocol is very similar. It was based and developed similar to the Montreal Protocol, but for the climate change issue. The goal is to limit emissions of greenhouse gases. And most of you might be aware that it is now, just very recently, in past month or so, the Kyoto Protocol became active because enough countries in the world signed it, but not the United States. So here is the situation in the United States. The current administration does not support it, but there are many different opinions inside the United States. Most of the academic community, the experts on climate, agree that it's a very serious problem. And so many people think that the United States should have signed the protocol. In fact, there is some activity. States like California or Massachusetts and the northeastern states are beginning to have regulations in spite of the federal government which require increased fuel efficiency for vehicles. So the situation in practice is that the United States will not sign the Kyoto Protocol, but what we are hoping, there's building enough pressure, some of it even from industry. We're working together with industry to have programs that will work together with Kyoto. Programs that will have mandatory limits to the emissions and not just voluntary, which is what the current situation is. This is possible and it is beginning to happen. Just clarify one more aspect of the Kyoto Protocol. The Kyoto Protocol is not designed to solve the problem. It's just a first step because it does not involve developing countries. It's only an agreement between the developed world. But it's a very important first step. The United States administration, the Bush administration sometimes says, aha, we don't want to do this because maybe China and India will not go along. But that, from my personal point of view, is not the right answer, because it's very important to show leadership. The developed countries first have to show that they can function limiting their emissions, and then it will be quite possible to work with the developing world. In fact, China has already very important programs for energy efficiency, not just because they worry about climate, but because they worry about the availability of fuels for their economy. Okay, so it works together. The economy can actually work well within these limits, and it's not necessarily the case, as some people claim, that the economy works against the environmental issues. They can actually work together. So in a nutshell, I have high expectations that even the United States will have important programs limiting emissions of greenhouse gases, and that's the only way that we're going to prevent this large risk of having serious changes to the climate that will have very negative effects on society. Perhaps there might be some positive effects in some particular places on the planet, but most of the effects tend to be negative.
More questions? Maybe take a break a little bit with the question from our audience by hand. Mm-hmm.
Okay.
Yes. It seemed to me that many scientists are already aware of serious condition of environment. From your experience, can you share with us how scientists could integrate their findings to benefit the majority of us, and how do we convince the government that this is the way to do or to go?
Right. Okay, that's a good question. Let me first stress something I tried to say in one of my last figures, which is that we have to separate science itself from the judgment of whether society has to change. What science can do is offer results showing what are the probabilities that there will be changes, for example. In some cases, almost a certainty that there will be changes. Even with air pollution, where we have so much evidence that there are these very serious health effects, we don't know who is affected. So we just do the statistics. Okay? However, scientists also have to act as individuals. They have to work with the government. They can give opinions not just as scientists, but as individuals. That's why my personal opinion is that it's very important to act on climate change. My opinion as a scientist is that there is a certain risk of what will happen if we don't do anything. So we have to learn as scientists to communicate with the government, but also with the public. We have to be able to explain what we do and how it benefits society. We use resources from society to do our research. So it's only logical that we should be able to explain clearly what are the uses of science. Although it's very evident, if we look historically, those countries that have invested in scientific research, their economies are the ones that have really worked extremely well. So there is little doubt historically that it is that investments in science are required. But there is a tendency for many scientists to be removed from communication with the public, to be removed from working with the government, and it's something certainly with environmental problems that should not be the case.
Any question from the floor? Yes, please. Maybe this question first because the frequency is much more.
Sure. You can just read it.
Do you think Kyoto Protocol is a promising agreement, or how is it possible to be success? What is your opinion about the protocol? I mean, Kyoto Protocol.
So read just the beginning of it.
Do you think Kyoto Protocol is a promising agreement?
Yes. Well, the Kyoto Protocol, as I just mentioned, it actually has a number of flaws. It's not a perfect agreement, but it is very important, as I mentioned, a very important first step. So I do consider it essential and very fortunate that there are enough nations in the world that have initiated the protocol itself. It has to be very flexible. It has to keep improving, and again, it's not designed to solve the problem, but it's designed so that it will be easier then to work together with countries like India and China. We have to keep talking to them. They also, these countries, the developing world, has to be flexible, and they have to be willing to change their ways. They cannot insist on using the same technologies that led to so much pollution after the Industrial Revolution. So everybody has to communicate, but that's where the role of scientists is very important. We tend to have much more agreements within the scientific world than within the policy world. So it is essential that we all work together for this. So the Kyoto Protocol can be very much improved. It's a complicated thing to get to work. It's even in Europe, where they are so much behind it, they are having problems with the actual goals and targets posed by the protocol. But nevertheless, the process is very, very important. And so that's why I hope the United States continues to work in parallel with that project to make it work.
Is it possible that the world's climate will change to the ice age again, like in the film Today After Tomorrow?
Okay, that's very unlikely. Of course, that's just a movie. But here is what happens. We know from looking at geological timescales, if we go back tens of thousands of years, that small changes in what we call solar insolation, the way we get energy from the sun, those relatively small changes led to ice ages, very dramatic changes in the climate of the planet. And greenhouse levels, carbon dioxide, went up and down. But what is unique about what's happening now is we have changes that are above those that we have seen in the last 500,000 years. 500,000 years ago, we had a different planet. The continents were in different places and so on, so the climate was very different. But in more recent times, we don't have any precedent of having such high levels of greenhouse gases. So we don't worry so much about an ice age, because that's going down. But we don't know. It's just a big risk what happens when you go the other way around. But a cautionary note, for what's the inspiration for that movie, is that we could change the modes in which the climate functions. An example being the circulation of the oceans. It could be that some parts of the planet will indeed get much colder. But on the average, the worry is that the temperature will increase. Some parts of the planet will get much more rain or much more snow, and whereas others will go dry. So we might well see changes that are unexpected, a change in the mode of functioning of the oceans. But it's unlikely that this will be really another ice age. That's not what is expected by climatologists. Nevertheless, we can have, particularly if we do nothing about the problem, if we increase the emissions without worry, we are risking very serious changes in the way even the oceans function.
Further from that risk is two questions. The first one is drinking water, which has been treated by ultraviolet method, can cause our health.
Can cause what?
Our health.
Oh, okay. There's apparently some more questions. Yes, the ultraviolet light can be very useful to treat water, even ozone itself. Okay, there are some water purification techniques that use ozone, and so that if I understand the question correctly, that those technologies are in fact beneficial for our health if you get clean water as a result of that. We just worry about increased ultraviolet exposure if the ozone layer is thinned. Or in some places, I don't think it's the case here in Thailand, but in places like the United States, sometimes it's fashionable for people to expose themselves to the sun to get a little darker. And so if there's no sun outside, they can go and expose them to ultraviolet lamps. That's not wise from the point of view of public health, because the risk of acquiring skin cancer is indeed a serious one. So that's not a very wise thing to do. Ironically, it's very important to have a little bit of ultraviolet radiation, at least in northern countries where they get little sun, because it's a source of vitamin D and so on. So that's a very interesting question. Just one more piece of information. You can see how humans evolved. Dark-skinned people more towards the tropics, very light-skinned people towards higher latitudes. And this was in response actually to the ultraviolet levels, because there's naturally more ultraviolet light closer to the tropics. Okay? So you need a little bit of ultraviolet, but we know that too much is certainly harmful.
Still stick with UV, ultraviolet. Is the method of emitting UV ray to build germs in toilet safe for humankind?
Yes, as long as humans are not exposed to ultraviolet, it is all right. There are also different types of ultraviolet, and it's shorter wavelengths that the ones that are in fact shielded by ozone. The ones that break, those we know that the light of those wavelengths, or radiation, wavelengths shorter than about 290 nanometers, is very efficient in breaking DNA molecules. And DNA molecules are the ones that are very important for your health. And there's a repair mechanism that has evolved in humans and in other ecological systems, so that the ultraviolet breaks down these molecules and they are repaired. But if the levels increase, sometimes the repair mechanism fails, and that's when skin cancer, for example, can develop.
Further to skin cancer, look like we have a serious question, but it's from random from our audience. Would one develop skin cancer if constantly being exposed to water treatment equipment, which use UV method?
I am not very familiar with the details, but I would imagine that in a normal water treatment plant there would be protection for the people that work there. Of course, it's only people that are exposed to the ultraviolet radiation that would be at risk. It's also particularly worrisome for the eyes. You can develop cataracts and so on. And that's why it's important to wear glasses, even in snow. At higher latitudes, it's important to protect vision from ultraviolet light. But I would imagine that it's something that is taken into account in water treatment plants, but it's not something I know very much about, how they function.
Do we need to do some research about this, especially
Probably,
in the
yes.
Tropical area, because of the impact of temperature on the maybe function of UV that related to our lifestyle?
Right, right.
Okay. The next question. Maybe the simple one, but I'm so pleased to inform our audience that it's a question from our high school student.
Oh, very good. Okay.
Yes. The first one, I don't know he or she interested in the mechanism that CFC react with ozone in the atmosphere.
Okay. That, of course, I could talk for a long time about that mechanism, but I'll try to summarize. Here's what happens. I had a little cartoon at the beginning. The CFCs themselves do not react with ozone, but when they are exposed to this very short wavelength radiation from the sun, the CFCs molecules break apart. The simplest CFCs are derivatives of methane. You have a carbon atom and it's combined with chlorine atoms and with fluorine atoms. So this light of radiation, short wavelengths, breaks the molecule and you get free halogen atoms, free chlorine atoms that are not combined with anything else. Fluorine atoms react very, very fast with ozone. Ozone is a molecule with oxygen atoms, has 3 oxygen atoms. So a chlorine atom very rapidly grabs one of the oxygen atoms of ozone and makes normal ozone. And you get chlorine monoxide, CLO, which then subsequently reacts with oxygen atoms. You get the chlorine atoms back. And that's why you have this amplification chain. But the chemistry is more complicated than this. It's particularly interesting at high latitudes because there you have chemistry occurring on the surface of ice particles. So we spent many years, and so did many scientists, doing experiments first in the laboratory, but then going to the atmosphere and making sure that our understanding was correct. And we believe we understand quite well now how the stratosphere functions, and that's why we were able to make predictions that could be verified. In contrast, the chemistry in a polluted atmosphere like Bangkok or Mexico City, you have many big molecules. It's much more complicated. So we have to do it a bit more like engineering. We cannot understand every detail, but we can get the general behavior of the atmosphere by making measurements and working with computer models, doing the things that chemists and meteorologists do together.
Thank you so much. I would like to inform our audience that even the Professor Molina found out that his background about mathematics is not that enough since your study bachelor degree, and he intended himself and decided by his own to further his study to fulfill the background. I'm so impressed, and I would like our students to follow your step in this direction. And of course, even the question from our high school student is, how to say, simple in the sense that you already explained before, but it's indicated that he interested and can follow your lecture. I'm proud of you, our student. And the next one, it seems that it's a concern. Are there any strategy to replace ozone if it's a whole?
Okay. This is something that sometimes comes to mind. Why not just fill the ozone hole with more ozone? Okay, here is The first problem that we have is that the ozone layer is made naturally with energy from the sun. The sun breaks normal oxygen molecules that you know are made of 2 atoms. It breaks them in single atoms, and then each single atom rapidly combines with a normal oxygen molecule, and you get ozone with 3 atoms. So how much energy from the sun is required to make the ozone layer? It turns out to be much more, several times more than all the energy used by mankind. So it's a huge amount of energy. We cannot compete with that. We don't have enough technology to really fix it. Other ideas are, if we cannot really make enough ozone because we don't have enough energy, maybe we can inject some chemicals, or we can remove some of the chlorine atoms. But it turns out that the atmosphere is so complicated that any attempt to solve it by putting more things there usually makes things worse. So the only thing that seems to be wise to do is not to release the pollutants. We don't have technologies to fix what's already released to the atmosphere. Also, it's not possible to remove the CFCs once they are in the air, because they only are there at parts per million. That means maybe 10 out of every 1,000 million molecules are CFCs. It's very hard to think of ways in which you could remove these molecules. So really the only practical thing to do is to stop emissions.
And how do you think government can better stimulate research and development at clean technologies such as solar energy?
Tell me the last part again.
Solar energy.
Oh, solar energy, yes.
Stimulate the research and development for clean technology.
Right, but a very important action that governments need to take and are taking, in fact the United States government as well, is to put resources in developing alternative energy sources. Solar energy is one such source. Unfortunately, the normal way to convert solar energy directly to electricity with solar panels based on silicon and so on, those are still too expensive, much too expensive to compete, say, with burning petroleum. However, solar energy can be used very efficiently in some countries like Thailand or Mexico, where there's plenty of energy. For example, to heat water, or in certain applications, not to generate electricity directly. But it's very important to continue doing research on other forms. One good example is wind. Wind generation of electricity from wind used to be very expensive, but enough technology has gone into this matter now that it is much cheaper now. It's beginning to be competitive with just using fossil fuels. But it cannot be the solution, because wind has problems. You cannot store the energy readily, and sometimes you run out of wind. So you have to use many different approaches, a whole variety of approaches: wind, biofuels, energy conservation is absolutely essential, and also carbon capture. It is very important technologies are being developed so that you can, for example, burn coal using new combined cycle gasification power plants, much different from the normal, very dirty coal-burning power plants. And those plants not only are very efficient, but the carbon dioxide can be captured. New technologies are being developed so that this carbon dioxide then is injected in the ground rather than released to the air. So these are all possible solutions. Even nuclear energy, which is so worrisome for society now, it's important to do more research to develop clean and safe ways to use nuclear energy, just to have one more option. It has many problems at the moment, but it's important even to have that option in the future, because it's one way to prevent climate change. Of course, one has to deal with the proliferation issue, nuclear waste, but those are problems that in principle can be dealt with.
Refer to your lecture in Mexico as a case study. With a dramatic short rigid of time frame, why the city leader decide to switch the motor vehicle to hybrid to cut down the emission?
Yes, a hybrid would be a very good solution. It's what we call leapfrogging. Namely, you could introduce these brand new technologies. Hybrids are getting there, but they are still more expensive. So we are actually trying to convince the government to offer incentives so that people buy hybrid cars. But they are not yet being produced in large amounts. There are some hybrid buses that are being tested now. So it's a very promising technology because it's so much more efficient. You get much more kilometers per unit of fuel burn, what we call the mileage, than with a conventional engine. So it's a very promising technology, but it's still very hard to convince the government to impose that because the price is still higher than that of a normal car. So it is, here again, the message is you have to use a mix of solutions. The brand new gasoline and diesel vehicles with state-of-the-art technologies, with these very low sulfur fuels, are really very clean already. They emit very small amounts of pollutants, but they still emit carbon dioxide. So we have to work towards increasing the fuel efficiency.
I think maybe partly the question really would like eager to learn more from the case study of Mexico in the sense that when we are almost the same in the sense of economy,
right?
We are not that rich. Why Mexico invests that much money for switch to hybrid?
Right. Well, here is what happens. It's important that we all talk to each other. So if something worked in one city in the developing world, we should use that example for other cities. That's why whatever we learn in Mexico can be useful here in Thailand or in China. And indeed, we are communicating. The question, why does the government invest more money in some cities and not in others? And that's a cost-benefit analysis. Okay? If the government really considers how much it costs for people to get sick, then you can convince them that these measures are important. But it's not very easy to convince the people in the finance ministries that they have to make these investments. We have to work very hard to talk to them.
See, further from this, because it's another question of what can we do with large industrialized countries which produce a large amount of CFCs and refuse to sign the Kyoto Protocol? Okay.
Here this question is related to the one we discussed before. First of all, the CFCs, fortunately, that part is solved. They are no longer being produced. But they still generate a lot of carbon dioxide, like in the United States, because you have these many big cars with very low fuel efficiency. So what one has to do is what we're attempting to do, to work with the government to impose regulations, not just to have it voluntary, because many people will not worry about it. We have to make the public aware that it's a risk. And hopefully we can convince the government to have regulations so that industry is forced to do that. And many industries are very willing to follow the regulations, provided all the industries have the same regulations. That's a problem with voluntary measures, because you cannot compete with others if only some of them take these measures. Okay? That's why the government has to put the limits, what we call carbon caps. There has to be an overall limit on the emissions of the country, and then maybe you let the economy judge which is the best way to do that.
I think maybe we really would like to learn more from you in the sense that once you, it's a fact-finding from your research about CFC, and then you bring attention or call attention from the media.
Right.
And how? Please.
Right.
Please give us some details.
Yes, well, with the CFCs at the beginning, it was very difficult. When we first were talking about our hypothesis, we had a problem because we were talking about invisible gases. You cannot see the CFCs. And they were affecting an invisible layer because you cannot see the ozone layer. And it was protecting us from invisible rays because you cannot see ultraviolet. So some people thought we were crazy trying to convince the public that this was a serious problem. But talking to the news media, talking to people in government with enough patience and conviction, we were able to really make a case that it was a serious issue, and that's how it eventually got solved. A very important step was also working with industry. Industry initially did not want to be regulated, but when they realized the problem was serious, and they realized if all of them have the same regulations, then it's okay. And so we're beginning to do the same, even with oil industry. Some big oil companies are willing to change, but it has to be all together. You cannot have only one or two changing, because that would be unfair competition with the others. Okay? So they are very eager to find also these new alternative energy sources, not just burning fossil fuels without capturing the emissions. Okay? So working with industry is one of the important lessons we learn from the CFCs.
And the tactful of communication with industry, how to communicate and convince them. I think this is the art and tactful.
Right. But what we do is we work with industry and we offer a neutral forum, industry and government. Okay? We have to do that together. There might be apparently, I don't know if there's a question from you.
I have a quick question.
Yes, please.
You mentioned that with the Montreal Protocol, you had a problem convincing people because everything is invisible and no one was really thinking about those things. It seems like a lot of the criticism from America's standpoint is that the global warming phenomenon isn't really proven, that there's no real evidence for it, and if there is any evidence for it, it will cost jobs and cost the economy.
Right.
I was wondering if you could use your knowledge of the Montreal Protocol to sort of discuss what you think was unique in getting it passed with worldwide support. You mentioned it was the only protocol that ever succeeded. Thank you.
Right. With the Montreal Protocol, we had a very strong scientific case. We don't think it's any more valid just to say that with climate change it's not proven. Politicians all the time have to make decisions in the face of uncertainty. There are very few things that are proven in life. So that's why I introduced the issue of risks. If there is a high risk that something will happen, you act on it. Let me give you an example. So this is why we have to work with people in government. The example is from public health. If you have a child and he has a tumor and you bring him to the doctor, to the physician, and he looks at the tumor and says, only 10% chance that it's cancer, don't worry. The parents would not accept that. 10% is huge. You would have the surgery and remove the cancer just in case. It's not proven that the child would die otherwise. Okay, so it's just an analogy, but we do not need a proof. We just need to make the case that it's a very large risk for society. And that's why I repeat, what the scientific community does is just present the risks as they see them, and then society decides whether to do something about the risk or not. The same thing happens in terms of the effects on the economy. If you are prejudiced against doing something about it, then you highlight that you will lose jobs. However, there are many examples. The CFC, in this case, is a good example. The economy did not suffer. The standard of living did not decrease. So we have very good examples of different countries using different amounts of energy per capita with high standards of living. The Scandinavian countries, for example, consume very much less energy per capita than the typical American citizen. And we cannot argue that they have a low standard of living. So here is where economists argue against each other, but one can make a very strong case that it is quite possible to have a vigorous economy. In fact, in some cases it's essential to work with issues like energy conservation, because if you neglect environmental problems, like was the case in the former Soviet Union, the whole economy collapses. So it is not easy, but that's why it's important to work with economists as well, to make a case that you have a holistic vision where the economy improves at the same time that you preserve the environment. And so we think it's not these points of view, as you express, that perhaps it's the way sometimes one envisions the U.S. current administration to think. We don't agree with that particular point of view. We think there are much better ways to function.
Another hand, please.
Yes.
Microphone.
Wait. I might repeat the question because we can't hear it. Right. Okay, here the question has to do with the following. A year ago there was a heat wave. The temperature went unusually high in Europe. And in fact, there was an associated increase in mortality. Many elderly people that are vulnerable actually died, just like they do when there is a high pollution episode. And the question is this connected with it's not really connected with the ozone hole, but it's connected with climate change. I have to be cautious here. A single climate event, we cannot claim that it's due to climate change. But if we look at so many things changing, lots of changes all over the planet, yes, we have a very strong case that the climate is changing. And I saw the temperature curves in one of the earlier figures. So yes, we have the very strong suspicion that whatever is happening is connected with human activities. We are almost certain now, there is very little doubt that the climate is indeed changing. What some people claim is that we cannot make a case that those changes are connected with human activities. But I couldn't go into all the scientific evidence, but we understand the way the climate functions. So there is a very strong indication that it is that, for example, the heat wave in Europe was indeed connected with climate change, in turn caused by human activities. And that's one example that points out why we should worry about climate change. It's not just that it will get a little warmer everywhere and will be nicer. It's that we have more extremes. And these extremes do affect society in very negative ways.
Such a lively atmosphere, and come to the last question.
Okay.
Is there any international organization like UN or World Trade Organization oversee or control the impact of human activities on density of the atmosphere, or is this strictly only to the research without any activities?
No, it is very important to have international organizations like the United Nations. The Montreal Protocol was really brought together by the United Nations Environment Programme, UNEP. They were the ones that can convene and can get countries all over the world to get together and ratify a protocol. What scientists can do, as they did with the ozone issue and they are doing with the climate change, you have international groups of scientists that evaluate the situation, and then they give their summaries to the representatives from the governments. And the representatives from the governments then make the decisions whether to have agreements. The scientists don't do that. And so the important precedent is with ozone depletion. We have this international group. With climate, it's called the IPCC, Intergovernmental Panel on Climate Change, which follows what happens with stratospheric ozone. This group makes reports every few years, and these reports, they summarize the findings, but they don't tell the politicians what to do. The last summary, they concluded that there was indeed very serious cause for concern, because all these changes we're just talking about were most likely the consequence of human activities. And then the United Nations, in this case together with the WMO, several international organizations are the ones that put together the Kyoto Protocol. Okay, so we do need international organizations. And the trade organizations, unfortunately, they sometimes have a different agenda, so we have to learn to work with them, because trade and environment in the long run have to work together and not against each other. So we hope that that's indeed something that can happen.
Oh, I have confidence that we learned so much, but time has run so fast, and we very much deeply appreciate the greatest honor receiving from Nobel Laureate for Chemistry in 1995, Professor Molina, who has had incredible experience and success, beside masterpiece of life. May I take this opportunity to invite Director, Environmental Research Institute, Chulalongkorn University, Associate Professor Dr. Thaviwong Siburi, to present a token of our appreciation to Professor Molina. Please, Dr. Thaviwong.
Thank you. Thank you very much. Oh, appreciate it. Thank you. Thank you. Thank you.
On behalf of Chulalongkorn University, we are very much appreciate your attend the special lecture, and we hope that you will join the next event again. It's a series that International Peace Foundation will cooperate with Chulalongkorn University. And for today, it's lovely enough that we learn a lot from both your life and your research work. Thank you for today. ขอบคุณมากค่ะ แล้วก็โอกาสหน้าเจอกันอีกค่ะ สวัสดีค่ะ
Thank you very much. Thank you.